So this is our lecture module on conservative vector fields and path independence. It's really about conservative vector fields, and that leads to a result for path independence of the line integrals that we've been doing so far. So far in this course, we've been doing these line integrals, and like I say, sometimes I call them line integral or a path integral or a contour integral or even a curve integral. They're all the same thing. Okay, there's no difference between these things. But one thing you need to have absorbed at this point is, just to be concrete about it, let's say we have some vector field, right? It's a function of x and y, and it's got some function p of x and y as an I component and some function q of x and y as a j component. The same basic results apply to 3D. It's just a little easier to talk about in 2D. The note module talks about the 3D case as well. It's just kind of a simple extension. We're not going to spend a lot of time on that. So we have this as our vector field. Sometimes I call these vector functions. Sometimes I call them vector fields. And is there any difference between the two? No. When we're doing calculus and we're doing functional analysis, then we tend to like to use the word vector functions because they're vector valued functions of real variables. Sure. When we're doing physics and stuff, we sometimes start to talk about them as vector fields because we're then talking about the physical interpretation of the field as a through space mechanism, maybe representation of how maybe forces interact at a distance. We think of there being a field in the between, and so we start to call these vector fields. But there's no difference between vector fields and vector functions. Okay. Now, so here we have a vector field. And we've got this idea that we're going to calculate along some curve C1 the dot product of that vector field onto the path components of this path. And the point I want to make is, in general, this depends on the path. So the same vector field, different path, gives us a different result. That should be not surprising, right? You have this field over space, and I'm going to add its value up as I walk around. Well, depending on where I walk, the field has different values, and I expect this to have different answers. But what we're going to talk about now, or deal with now, is a special case. It's a small subset of these vector fields that are what we're going to call them conservative. So they have certain properties. And the thing that starts to happen is, if you have a physical vector field, well, there are physical laws that it has to obey or that it's starting to try to represent. And you might have, like, if you have a non-compressible fluid and it's flowing, well, in some part maybe where its flow elements are coming together, you might have a decrease in some component of a vector that then requires at another position an increase. So if it compresses here, it expands there. That kind of thing. I'm being very loose and non-exact about that. But physical reality will place constraints on a vector field sometimes that may make it conservative. It is not the case that all physical vector fields are conservative. The magnetic field is generally, even in magnetostatics, not conservative. We'll get to that at the end of the module. This is kind of a long module in terms of page numbers, but in terms of discussing it, it's not really all that long. Okay, this is our general case. Okay. Now, as we move on to this special property of conservative fields, I want to remind us about something. Okay, so let's look at this thing here. Okay, this, in a certain extent, should seem familiar. Okay, so this is the fundamental theorem of calculus. If you're doing an integral along a straight line in this case, but as we move along dx, if you're doing this integral and the thing you are integrating happens to be equal to the derivative of some other function, then this whole summation, this integral, just turns into the function whose derivative is the integrand, that function evaluated at the endpoints. And we don't worry about the in-between. All we care about is the endpoints. Okay? When you learned about this, it didn't seem unique or special. But the point I want to make here now is, see, this thing we're integrating had to have a property. It had to be the derivative of something. And when you do first year calculus, you start to get the impression that every function is the derivative of something else. In other words, you can always calculate an antiderivative, or at least you might start to get that sense. But there are functions, and in the notes I mentioned, a very, very popular function. It's essentially strongly related to the normal distribution, the Gaussian distribution for statistics. But there is no function whose derivative is this. Okay? You can't calculate an antiderivative for this function. And it's not all that complicated a function. So it's not the case that this is always true. Well, sorry, this is always true, but not all functions are equal to the derivative of something else. So the point is, when we're doing this integral, if this has a certain property related to it, a derivative of it, then you have this simple result. Okay. So what we're going to do now is, I'll say expand this to our vector calculus approach to a line integral. That's probably a strong word for it, but I'm making a connection to the two. Okay, so this is what we're going to have. Okay, so we'll let this be the same. G is equal to this function here. Okay. Then we're going to say if G is actually equal to the gradient of some potential function, if that's the case, then the integral of C G dot dr is equal to the integral of C, well, gradient of phi dot dr equals phi at B minus phi at A. Okay. So look at the relationship. I've got this integral along a line now. This was just a 1D integral. This is integral along a line. But what's this? This is a derivative of something. So this thing that I'm integrating is the derivative, a special kind of derivative, but the derivative of something. And if that's true, then this whole integral is just equal to that original thing evaluated at the endpoints. So it's very similar to the flavor of the fundamental theorem of calculus. Okay, where A and B are the endpoints of the curve C. If this is true, then we're going to call this vector field G conservative. And then the really important thing is there are 4 equivalent statements. Okay, there's 4 okay. In other words, if any one of these 4 things is true, the other 3 must be true. Okay. So, number 1. G equals the gradient of phi for some phi. That means G is conservative. Okay, so this is the thing. If G equals the gradient of a scalar, and not every vector field is equal to the gradient of some scalar. Okay? If it is, it's conservative. If that's true, then this would be true. That means the curl of that thing must be 0. If the curl is 0, this must be true. If this is true, this must be true. Okay? This is actually going to be our test of conservativeness. If you're just looking at an integration and you've got this vector field and we have to decide whether it's going to be conservative, we're actually going to do this. We're going to calculate its curl and check if it's 0. And if it's 0, then we know we've got a conservative field and we can do our other things. So this is very important, okay? Mechanically or practically. The third thing that must be true, if any of these is true, is that this contour integral of G dot dr is path independent. It doesn't matter what curve we take between point A and B, the value will be the same. Okay? If that's true, this is true. If this is true, that's true. So this is all 3 of them together. 4, if we take the closed contour integral, so if we integrate G along a line, there's a closed path. So we start at a point and come back to that point. This will be 0 for every closed path. these two go together and these two really go together, right? If this is path independent, that means it's only dependent on the endpoints. But if it's a closed contour, the endpoints are the same. So if this is going to be equal to the difference in phi at the endpoints, but here we have the same endpoint, this must be 0. So these two are kind of almost the same thing. Knowing one directly gives you the other one mathematically. The curl of G being 0, we showed before, and you can show, we noted before, we didn't prove it, but you can prove that just mathematically, the curl of any gradient is always 0. Okay? You could expand this out for an arbitrary function phi, work this all out, and you'll find that it must be 0. Okay? So these two kind of mathematically are the same. But the real power now is this thing implies this thing. Okay? And this is going to open us up to two ways to solve or calculate a line integral. And this is a stereotypical question type that we have on the midterm and final exam. And I love it for a couple reasons that I'll explain while we talk about it. Okay. So, let's just I'll show one of these. Well, yeah, sure. Okay. So in the notes I say, determine, example is, this is if f equals x squared minus 2y cubed I plus x plus 5y j is conservative. Okay? So that means, is the curl 0? So we take the curl of f. I, j. Okay, we'll talk about this. Di x, di y, di z. And then we have x squared minus 2y cubed. Then we have x plus 5y and 0. Okay, a couple things. What is this notation here? So this is just a shorthand that we use sometimes. I certainly use it. Okay, di sub x is di by di x. Okay, when we get to writing a lot of these things, we'll say that. Okay, more importantly though, why am I going and writing the full three-dimensional curl if I know I have a function of only x and y? I do it just because I can remember that most easily, right? The curl of f is always equal to this. Now, it's true that when a function does not depend on z and has no z component, the I and j components of the curl will automatically be 0. But let's just pretend we don't realize that. So we go to I, we can talk this, so we go di by di y of 0, that's 0, minus di by di z of this function of x and y, which is also 0. Okay. Then I do j, so I take away this row and this column, and I go di by di x of 0, that's 0, di by di z of this function of x and y is 0. Okay. Then I finally get to k, so now I take what's left here. So I take di by di x of x plus 5y, which is is 1, minus di by di y of this, which is minus 6y squared. Okay, so I had 1, and this is minus 6, and this is not equal to 0. Okay, so this vector field is not conservative. Doesn't mean it's not physical, doesn't mean it can't exist, just means it's not conservative. Okay? Because every component of the curl has to be 0 in order for it to be conservative. That's all there is to this. If someone says, is this conservative? You generally test it by taking the curl. Okay? Now, in the notes, I then do another example where we show that that is the case. You can follow that through in the note module itself. Okay? Because I want to get to just doing a full problem here. Which I'll end this module recording and do it in a separate recording. It's kind of half related to this. Okay. Just one more note before we leave this module is let's talk about 3D for a second. It's really not that different. Okay, I've got G as some P plus Q plus R. Okay, these are all functions of X, Y, Z. Okay, so this is my vector field. And I have my R vector. Maybe I think of it as parameterized by T. This defines the curve C, is going to define the curve C. Okay. And the idea that the question of whether this is conservative is the same thing. You take the curl of G, and now I have P, Q, R. Okay? And now I have a set of relationships for each of these. Okay? But you don't have to memorize those. All you have to memorize is that this equals 0 implies conservative. Notice that all these statements we had on this side, none of these are specific to 2D. Saying that G is equal to, this vector field G is equal to the gradient to some scalar, that could be 2 or 3D. There's nothing specific to 2D here. This can be 2 or 3D, nothing specific to 2D there. This could be 2 or 3D, this could be 2 or 3D. So all these statements are exactly the same. It's just that when we're dealing with 3D, the question of being conservative gets a little more complicated, just in terms of the number of terms that you have to talk about. Okay. Okay. So now I'm gonna, when I end this module, I'll move on to talk about just look at a certain example. But what I want to talk about for a minute here is, and I'll just do this quickly because at the end of the module I talk about this more slowly, is it's time to connect these things to some things that you've heard of or looked at before. Okay? And they're different. So one set of differential equations expressed in the language of vector calculus that governs a sort of a physical set of phenomena would be Maxwell's equations. Okay? And let's just, they often have names. There's Gauss's law, there's Faraday's law, there's Ampere's law, then there's the no magnetic monopoles law, right? But they all are expressed in terms of vector calculus. They have a differential form, they have an integral form. And I want to just look at the integral form of a couple of them, because now that we've talked about what we've talked about, you can see some things now based on the language that we've used so far. So let's, just for a minute here, let's talk about Faraday's law. Okay, so the more general way to express Faraday's law. So Faraday's law, like physically says, okay, I got this region, through which this region I have a time-varying magnetic field. If I have a time-varying magnetic flux through that surface, I'm going to have a tangential component of electric field around that surface. That's the statement of Faraday's law. But saying that mathematically is saying I'm going to integrate E in a closed loop around a region that itself encompasses a surface that has a perpendicular component of B integrated over that surface, and if that time variation is non-zero, this electric field integral will be non-zero. This is a general statement of Faraday's law. Now, we haven't talked about this stuff yet. We will pretty soon. We do 1D line integrals, then we're going to do 2D integration, then we're going to do surface integration. So this kind of thing is coming up pretty soon. But we haven't done that yet. This, though, we have. We know what this means now. Now, if we have what we call electrostatics, that implies that there's no time variation, no significant time variation. Okay? That means that this thing is zero. So in the electrostatic case, E dot dl around any closed loop C is zero, regardless of the C. What does that mean? We have it over there. This means that in this regime, E is conservative. That means E can be written as the gradient of some scalar function, which we call units of voltage, of volts, right? The electric potential. Now, when you're doing electromagnetics, and you guys really won't do your next serious electromagnetics course till next year, you often start here. You say, well, E is equal to the gradient of a scalar. And that potential function is very important. That's a practical means to solve many electric field sort of problems. But the point I'm making here is, this is our general physical law. In a certain regime, where the time derivatives are zero, say, this simplifies, and in that regime, E becomes a conservative field. If E is conservative, it's equal to the gradient of a scalar, and now it enables us to do problems a certain way, okay, which is powerful. The other thing I want to say is, so it's not the case that the electric field is always conservative. In a certain regime, where time variation is insignificant, the electric field is conservative, and it's equal to the gradient of potential function, and we can find that. But as soon as time variation starts to kick in, then that ceases to be true, and E is not conservative. So conservative doesn't mean a physical field. It's just that some physical fields are conservative in certain circumstances. Probably more generally, normally, this is Ampere's law. Okay? Again, probably not the way, not the mathematical way you've seen it expressed. Right? So the idea here was, if you had a wire or anything carrying current, right, and you took a loop around that in the direction of your finger's loop, you would have a magnetic field circulating around this current carrying wire, and the integral of that B over this entire loop was equal to mu naught times the enclosed current. Okay? But again, it was a line integral that was actually being used for Ampere's law. Now, here, so B in general, when there's currents around, which are the fundamental, one of the simpler ways that you think of a magnetic field being created. Charges result in electric fields, currents result in magnetic fields. Yes, time-varying electric fields cause time-varying magnetic fields, vice versa. That's sort of a second layer of the onion when we talk about electromagnetics. So, but even in the magnetostatics case, there's current, okay? So in general, B is not conservative. The curl of B is not zero. B is not equal to the gradient of some scalar. And that's why when you're doing introductory electromagnetics, you do not spend any time, or not much time, dealing with the scalar potential for the magnetic field. There is a way, there is a condition. If there is no current through the loop or no net current, then the magnetic field can be conservative in that situation. It's just not as common as this one. Okay? My point is, all the mechanics and the language and the notation that we're working up in vector calculus are needed to do serious electromagnetic work. Lots of other cases too, lots of fluid flow, Navier-Stokes equations, they require a vector calculus approach. In NMM 3415, where we do partial differential equations, they're all cast, whether it be the heat equation, the wave equation, diffusion equation, which is like heat equation, what else do we do? Laplace's equation. They're all cast in a vector calculus notation, okay? Because that's where we get real power to deal with these sort of physical situations. Okay? So the next module, I'm just going to show you a stereotypical example problem that we can now do once we have a test for whether a vector field is conservative or not.